Welcome to lecture. This is going to be an algebra review, and we're going to be reviewing, this is review lesson 6 of complex numbers. So, complex numbers, we're most familiar with the term imaginary numbers. I think most of us heard that. I like the term to use the generic term of complex numbers, but the imaginary number, is just the I, and we're going to see that it's just the square root of -1. We need that as a placeholder because later on we can do operations with that as well. We just don't have a good representation. I seems to be a good use. So in our study of algebra, so far we've worked exclusively with real numbers. As we encounter new types of equations and new applications, we need to look outside the set of real numbers to find the solutions. Remember, we have been looking at all real numbers is what we've kind of worked with so far. Remember when we had x squared equal to 1 and we took the square root of both sides? We had two solutions of that, 1 and -1. But what about if I've got the equations x squared is equal to -1? There's no real number x for which if I square it, I'm going to get -1. If it was 1, 1 squared would be +1. -1 squared would be +1. So I don't have any real number solutions that I know of yet. So what we do is we just define an I, a new number I, such as I squared is equal to -1. And then we maintain that as a placeholder. If we square it, we've got back our -1. So we're where it should be, and that's how we're going to work with. Okay. So the number I is called an imaginary number and is used to represent the square root of -1, a placeholder. Furthermore, the square root of any negative real number is an imaginary number that can be expressed in terms of I. So here we've got the imaginary number I. I is equal to the square root of -1 down here, and I squared is equal to -1. If b is a positive real number, then I can have negative b being I times the square root of b. Okay, so in case if I had something like x squared is equal to -b, then my x would be I times the square root of b. So here is a few of these things, square root of -25. If we look down here at the solution, we can see we want to represent that at first as -1 times 25, the square root of -1 times the square root of 25 for my radical properties. And the square root of -1, I just represented I, and then I'll look at the square root of 25, well that's just 5 in this case. So I can write that as 5I, 5 times I. If I square this number, I get 25. I squared is -1, so -25. I recover that -25. For b, the square root of -12, I'm just going to simplify a little bit. There's that negative, that I that I take out as the square root of -1, and then I just do my radical operations on the square root of 12. 4 times 3 is 12. The 4 I can take the square root out as 2, and then I'm just left with the square root of 3, which I can't do anything with. Square root of -13, I take out the -1, the square root of -1, that's my I, and then the square root of 13 I just leave alone, so I can represent it either way, I times the square root of 13 or the square root of 13 times I. I tend to do this, represent it in this way, something times I. Okay, square root of 13 times I. So you could stop and take a look at these, see if you can get these worked on. So here's the properties of the radicals that I mentioned before. If I had two square roots, square root of a times the square root of b, I could combine them, square root of a times b. And here if I had this -1, I'm working backwards, the square root of -1 times whatever that the other number is. And recall, if I've got this, if I've got a rational expression, square root of a divided by the square root of b, that is the same thing as the square root of a over b. So for this reason, we write the radical expression in terms of I first before applying the multiplication or division property of radicals. For example, I would want to represent this as I times the square root of 9, I times the square root of 25, then I got 3I times 5I, 15I squared, which is 15 times negative 1 of 5 if I simplify this. So I get my negative 15. Here I'm going to do the same thing. I'm going to take out the I first. Now note if I hadn't done this correct. If I'd have done just taken the radical and multiplied the negative 9 times the negative 25, I'd have got the negative 1 times the negative 1, I'd have the positive, and then I would have had the 3 times the 5, I would have had a plus 15. Here the same thing, I'm going to take out the I from each expression, the top and the bottom, but here I can cancel out the I. So I get square root of 50 divided by square root of 2. Now I can do these properties with the real numbers and get this to be 5. So by definition, I squared is equal to negative 1. But can I do other powers of it? Well, it turns out that I've just got a couple of things, and I just basically use the definition, and I can do all kinds of powers for this thing. I can reduce powers all the way back down. So here we just represent all the powers up through 8, but you'll see this kind of repeats. I to the first power, that's just I. It's understood first. I squared is negative 1. I cubed I represent as I squared times I. The I squared I replace with negative 1. I know what that is. And now I just got negative 1 times I, which is negative I. So I cubed is negative I. And now watch, if I take the fourth power, I squared times I squared, I have my negative 1, I squared is negative 1, I squared is negative 1, and then negative 1 times negative 1 is just 1. I to the fifth, we're going to see now that we repeat, I to the fifth is just I to the fourth times 1. Every time I say I to the fourth, that's just 1. Now I've got the I, so that's just 1I, negative 1, this is 1, negative 1I, negative I, and then I to the fourth is just 1 times 1 is 1. So notice that even powers of I simplify to 1 or negative 1. If the exponent is a multiple of 4, then the expression equals 1. I can divide by 4. Whatever power I've got, I divide out the 4. So now it's just all the fourth. The whole numbers in the fourth is the plus 1. And I just need to look at the remainder to see how to handle it. So that's just basic, the imaginary number. That's for the I by itself. Complex numbers are all the things that we can combine with an imaginary number as part of it, and we'll see how that goes. So we now define a new set of complex numbers. I'm going to get rid of me, and let's just continue with the lecture. We now define a new set of numbers that includes the real numbers and imaginary numbers. This is called the set of complex numbers. So a complex number is made up of a real part and an imaginary part. Given real numbers a and b, a number written in the form a plus bi is called a complex number. The value a is called the real part of the complex number. The value b is called the imaginary part. So all of the imaginaries that we have seen really is a complex number with a equal to 0 and b is the imaginary part. So just the pure imaginaries are complexes as well. So if b is equal to 0, then a plus bi equals the real number a. This tells us that all real numbers are complex numbers. So there's a bigger set than the real numbers, and that's called the complex numbers. And the real numbers are just a subset of the complex numbers. If a is equal to 0, b is not equal to 0, then a plus bi equals bi, which we say is pure imaginary. So 4 plus 0i is generally written as the real number 4. We usually don't carry this around, and that's just the real number. So once I get this complex number in this form a plus bi, that's the standard form. And what we want to do is to find operations that we can do. We can do the same thing on complex numbers as we do on real numbers. What are those? The addition, We can do subtraction on real numbers, we can do multiplication, and we can do division. Those are our 4 basic operations, and it turns out we can do those on complex numbers as well. So to add or subtract complex numbers, I've got 2 separate ones. All I have to do is just add the reals. So I've got a plus bi plus c plus di. I'm going to add the a plus c, and then the b plus d is part of the imaginary. So I handle this just like if this was an x. I group them together. So I'm grouping my real part, and I'm grouping my imaginary part. If I define a plus bi minus c plus di, I have to do this with my distributing my negative number. So it's a plus bi minus c minus di. So I've got my a minus c for my grouping after I simplify. And then b minus di is my complex part, or my imaginary part. If I multiply, so addition I just did, now I want to multiply. I've got them in standard form. I've got 2 of these things right here, negative 2 plus 6i, and I want to multiply that complex number times 4 minus 3i. So I'm going to do the very same operation that I do on mathematics. I'm going to do distribute on my real numbers, distribute, distribute, and now distribute, distribute. Okay, so negative 2 times 4, negative 2 times negative 3i, 6i times 4, and then 6i times negative 3i. I just have to make sure I keep up with my signs. The negative 2 times 4 is my negative 8, plus 6i. 4 times 6 is my 24i. And here I've got my minus 3 times 6 is my minus, it's 18. But I've got an I times an I, that gives me my I squared. So this is the result of the multiplication, but we can simplify one step further, and we always want to do this. Anytime I have an I raised to a power, I want to go back and represent those to what we already know, what we looked at just a second ago. I squared is negative 1, so I replace that. And then I've got negative times a negative as a positive, and now I can group those with my constants, my real part, which gives me 10 plus 30i. And I always want it in terms of a plus bi. I don't want to have any exponents as far as my in my I. Here's a couple of more. 3 plus 4i squared, that's just 3 plus 4i times 3 plus 4i. And remember, I continuously look at this in class when I expand to a plus b squared. Square the first, multiply the 2 together, and then double it, or times 2, and then square the last. I want to do this the very same way. 3 squared, multiply the 2 together, 12i, but then I'm going to double it times 2, and then square the last thing. So that's a 16i squared here. I squared, remember, I don't want anything with the squared, cubes, any other power except the 1. So I replace that down to negative 1. 9 minus 16 is my negative 7. Here I've got this. I've got the difference of 2 numbers, plus or minus. Remember, the difference of 2 squares is a plus b, a minus b. This is the same thing. Here I'm going to call this the complex conjugate. So a complex conjugate is the real part plus or a minus, and then the conjugate part is the opposite sign. So here I'm going to apply the property a plus b times a minus b is equal to a squared minus b squared, the difference of 2 squares. It's just square the first, square the last, and the I squared here, this is 4, 2 squared I squared. The I squared is negative 1, so it turns out to be, instead of negative here, it turns out to be positive. So this is just 29. I just have to remember not to do to have the I squared, and I replace that. So the complex conjugate, the product of complex conjugates, this is the conjugate of that, that is the conjugate of that. If a and b are real numbers, then if I multiply complex conjugates together, all I have to do, if I can remember, is just a squared plus b squared. If not, I multiply them out, and I just have to remember a squared is my negative 1 to simplify. So those were our multiplications, and now that's it. We knew how to add, we knew how to subtract complex numbers, we know how to multiply, What about division? I'm going to turn division into a multiplication problem. So what I have to do is try to get rid of this, turn this into a real number. Okay. So this is how I do it. And I use this little fact of complex conjugates to do it with. So I want to divide a plus 2i by 3 minus 5i. What I'm going to do is turn the bottom into a real number. You remember, if I multiply times the complex conjugate, this turns into a real number, a squared plus b squared. So whatever this sign is, I'm going to do the opposite sign. But whatever I do to the bottom, I've got to do to the top. So I do this on both of them. So I multiply these two. I know how to multiply. And this, when I do the product of complex conjugates, that's just the 3 squared and the 5 squared. Here I multiply out, distribute, 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 distribute. I squared is -1, so that makes that -10 plus 24. There's my 14. I've got my 46i, and now my 9 plus my 25 is my 34. So anytime I have an a plus bi divided by a number, remember that's just the 14 over the 34, plus this 46 is over that very same 34. So we looked at solving quadratic equations in previous lessons. Now we're just going to look at seeing another class of quadratic equations with imaginary solutions or complex solutions. Okay. So we're going to solve quadratic equations over the set big C, or complex numbers. Okay. So I want to look at this. Solve the equation by applying the square root property 2y squared plus 36 is equal to 0. So here I'm going to isolate the y squared and take the square root of both sides as my game plan. Subtract 36 from both sides. Minus 36 minus 36 gives us this 2y squared is equal to -36. I don't want to do this with the 2. I want the 2 over there, so divide both sides by 2. That gives me the -18. Now I want to do the square root property. Take the square root of both sides. And remember, I have two versions. When I do this, plus and minus, the square root of -18. That's -1 times 18. So I take out the -1 as an I, square root of -1. I'll leave that alone. This is 3 times 6. 2 times 3, 3 times 2 times 3. So I can take out the 3 squared as a 3, and then I'm just left with the square root of 2. So that's just a simplified radical. And there's our solution set. Plus or minus 3i, which is plus 3i on the square root of 2, minus 3i times the square root of 2. So we can look at, if we've got the quadratic equation in its general form, ax squared plus bx plus c. And remember, we had the quadratic formula, x is equal to -b plus or minus b squared over minus 4ac all over 2a. This thing up under the radicand, right up in here, b squared minus 4ac, is called the discriminant, and it basically tells us what kind of solution we're going to have. It's going to tell us the number of solutions. It's going to tell us if we have one solution or two solutions. And then it's going to tell us if they're real or complex. So we're going to examine 3 different cases here. So I've got this. I'm going to look at this is what I'm looking at each time. And in this case, when I look at b squared minus 4ac, I'll do this calculation first. If I needed to do this, if I'm going to do the solution, I need to calculate that anyway. So I'm going to do it first, and that's going to give me an idea of what I'm talking about. If all I need to do is the number and types of solution, I'm finished. -31, that tells me I've got 2 solutions. I would have, like, if this was the equation, 2x squared minus 3x plus 5, the b squared, this is a, b, c. If I do this, this is -31. So I have this as an I can take out the I square root of 31, but I have 2. I have 3 plus I times the square root of 31 over 4, 3 minus I times the square root of 31 over 4. two solutions because of this, plus and minus that. So if this is less than 0, I have no real solutions. They're both complex. If b squared minus 4ac is equal to 0, I have one real solution. So here's x squared plus x squared plus 6x plus 9 equal to 0. My b squared, there's my a, b, c, b squared minus 4ac, 6 squared minus 4a, 9, and that turns out to be 0. So when I do this, the square root of 0 is 0, so I have no plus or minus. Negative 6 plus 0 is negative 6, negative 6 minus 0 is negative 6. So I have the one solution x is equal to negative 3, but I like to carry along the idea of its multiplicity. It has multiplicity too. Later on we're going to refer to that as how many factors need to be there when we're actually representing the quadratic as a pair of factors. b squared minus 4ac greater than 0, I've got two real solutions. So here's an example, 2x squared plus 7x minus 1 equals 0. I do the discriminant b squared minus 4ac, I get 57. Well, that is our real solution. Since that is positive, I can take the square root. I've got plus and minus those versions, negative 7 plus the square root of 57, negative 7 minus the square root of 57, and both of those are over 4. So here's a couple. There's in the slides that you can go over. Here's the 5x squared minus 3x plus 1 equal to 0. I'm just looking at b squared minus 4ac. This one's negative 11. So that would tell me I have two solutions. They are complex. And they're complex conjugates. Okay, because I have one plus I, one the minus I version of the square root of 11. Here I'm starting out with 2x squared is equal to 3 minus 6x. Remember, when anytime I have a quadratic, I recognize the square, I need to have it set equal to 0 to solve. That's the only way I can solve these things. So I set them equal to 0, get everything over on the other side. b squared minus 4ac, I'm looking at the discriminant. I've got a real number, so I've got two real solutions. 4x squared plus 12x is equal to negative 9. Again, set them equal to 0. b squared minus 4ac, I'm just looking at the number and type of solutions. Here I get 0, so I have one solution. It's real. Multiplicity 2 for later on. So now that we've learned to solve all types of quadratic equations, both over the reals and the complex numbers, we can handle anything that anybody throws at us. But now I just want to look at something that looks to be a little more complicated, but we can still use what we already know. Here is an equation. I've got 2 plus 3 over x squared, quantity squared, minus 2 plus 3 over x minus 12 equal to 0. So what I want to do is recognize this in what I call a quadratic form. It's an equation in a quadratic form. This and this is the same. I've got something squared minus some multiple of something minus 12. So if I kind of let u is equal to 2 plus 3x, I'm just doing this as a placeholder so I don't have to think of this all over. This looks just like u squared minus u minus 12 is equal to 0. I can solve this for u. But what I have to do is remember that u is equal to whatever that solution is equal to 2 plus 3 over x, and then I have to solve for x. Here is another typical equation in quadratic form. 2w to the 2/3 minus 3w to the 1/3 minus 20 equals 0. So here I see that this is this squared. Again, this is this squared. Square this, I get the 2/3. So if I let my u be equal to w to the 1/3, and this just comes through practice, of just recognizing what I'm going to do as my u, do this little change of variable, and this looks like now 2u squared minus 3u minus 20. I can solve for u using my quadratic techniques, and then I just remember that u is equal to w to the 1/3, cube both sides in this case, and I would have my w. So the equation on the right are quadratic, easily solved. Then I use back substitution. That's basically taking this number, sticking it back in, and solving. So here's a full example of this. So if we have 2x squared minus 3 squared plus 36, 2x squared minus 3 plus 35. This is if I squared this thing out, I'm going to have what? 4x to the fourth, and I'm just going to have it's just going to be too hard or too complex to look at. But if I recognize this is this squared, I'm going to let the u equal to this, all of this stuff in here. U is 2x squared minus 3, and I can simplify this form down to this. U squared plus 36, this is my u, plus 35 is equal to 0, and I solve that. This I can factor. Two factors of 35 that add up to be 36. Both signs are plus. U plus 35 and 1 does that for me. So here I solve for u is equal to u plus 35 equal to 0, gives me the u is equal to negative 35, or my u is equal to negative 1 from this factor. And now I just recall that 2x squared minus 3 is my u. So now I just go through my solution. In this case, I can isolate, divide by 2, and do the square root property. X is equal to plus or minus the square root of negative 16, which is plus or minus 4, and there's the I. If u is equal to negative 1, then I get the 2x squared minus 3 is negative 1. 2x squared is equal to 2. X squared is equal to 1, and then x is equal to plus or minus 1. And then there is my solution set. I need to go back and check all of these things out and then verify. But they all checked in the original equation, and there's the solution set. So here's this one. 2w to the 2/3 is equal to 3w to the 1/3 plus 20. I need to get them all over on the side there. It's not a linear equation, so I need to get them set equal to 0. Anything that's not linear, I need to have set equal to 0. So everything over on one side, and then I can take a look at it. So here I see that this is just the w 1/3 squared. That's what that is. So my natural change of variable is u is equal to w to the 1/3. So now I've got 2u squared minus 3u minus 20 is equal to 0. And then trial and error factor. 2u and u gives me the 2u squared. I need something in here. All the things, once I do all the calculations, I get the negative 3, and that would be plus 5 minus 4. 2u squared minus 8u plus 5u is the negative 3u. The plus 5 times minus 4 is the negative 20. So my u, when I solve this equal to 0, that's equal to 0. U is equal to negative 5/2, or u is equal to 4. But u is equal to w to the 1/3. So here I need to cube both sides. 5 cubed over 2 cubed, and that's a negative because of an odd power. W to the 1/3 is 4. I cube both sides, and this solution is 64. Both solutions check if we put that back in, and the solution set is the negative 125 over 8, or the 64. Okay. So that's the end of this lesson. Go back and review as you need to, and we'll see you next time.